So, I am going to plot the Bode plot of the 3-stage amplifier. So, this is log magnitude of the loop gain, 20 log magnitude of the loop gain transfer function, and this is log omega, right, or omega on the log scale basically, right. So, so what happens? Let us say this is omega 1. The third order loop gain function is A1 cube f. So, this basically must be (20 log A1 cube f). Beyond omega 1, what happens? 1 plus s over omega 1 the whole cube. So, every pole beyond omega 1 will fall at 20 dB per decade. You have 3 poles, so it will fall off the Bode magnitude plot, asymptotic magnitude plot will fall off at minus 60 dB per decade. So, basically let us assume that this is 1 decade, so this is 2 decades, and this is 3 decades. Okay, so this basically this is basically the this is the magnitude response of the loop gain function. All right. So, clearly this is a problem, right, the third order response is a problem. Now, if you somehow take, I mean remember that we said that a first order forward amplifier is unconditionally stable. So, if you somehow make a third order system look like a first order system, then perhaps that new system will inherit the good properties of the first order system, right. So, how do you make a third order system look like a first order system? What I mean, what is a first order system? I mean, the Bode plot of a first order system, how will it look like? It falls at minus 20 dB per. So, how can you make a third order system look like a first order system? Okay, well, the mathematical answer of course is one thing that suggests itself. You say, hey, if I make that 3, if I make that 1, right, then it will look like a first order system. So, if I have to make that 1, what should I put in the numerator? You multiply loop gain of s with 1 plus s over omega 1 the whole square, right, and hey, it seems like all our problems are solved, right, you get a first order loop gain function. But what what is the gain of this 1 plus s by omega 1 the whole square at infinite frequency? It is infinite, right. So, it turns out that you cannot basically multiply by 1 plus s over omega 1 the whole square, because that block would have to have a gain of infinity at at omega equal to infinity, which is not feasible, right. So, that is that is basically not possible, right. Okay. So, let us put that aside. What else? Now, how do you make this look like a first order system? what can we do? One minus, why? No, that is what he said, no? Multiply with 1 plus s by omega 1 the whole square, so that you can knock off 2 of the terms in the denominator. Yes, people. Okay. All right. So, I mean, see, okay, here is a pen, right? Let us say I want to make it shorter, okay, without touching the pen. What should I do? I mean, one way of making it shorter is cut it and then, you know, this thing, I mean, that is going to ruin the pen. So, I do not want to do it. I want to make this shorter without actually physically breaking the pen. What will I do? Yeah, put this by the side, and all of a sudden this looks smaller, right? So, by the same token, I mean, well, if I deliberately introduce another pole, right, here, say at a frequency which I will call omega sub d, where omega sub d is much smaller than omega 1, right. So, that is idea 1. You multiply the loop gain by another pole, except that omega d is much smaller than omega u, omega 1. So, what happens to the what happens to the Bode plot of this modified system now? It will fall at minus 20 dB per decade, very good, and it will keep falling, okay, and then it will continue to fall. Or let me choose maybe a little. Let's say I choose omega d here, much smaller than omega 1. So, what happens to the okay. So, you can see that, I choose, sorry about this, let us say I choose something here. Okay. So, if I played a trick on you and just showed you only this part of the picture, right. If I showed only that part of the picture, what what would you conclude? You would conclude that it is a first order system. What would be the unity gain frequency? Pardon? A1 cube f times omega. Okay, all right. And so let us say this is 0 dB. So, as far as the I mean, if I only showed you the part of the picture in blue, you would not be able to distinguish whether you would not be able to figure out whether this is a true first order system or a fake first order system. This is actually a fourth order system which is behaving like a first order system over this frequency range, correct. Okay. It is certainly not a true first order system, okay, because a true first order system would have a response which continued on to 0 always at minus 20 dB per decade. But what happens to this fake system? The fake system's magnitude response basically beyond omega 1 actually goes off as at minus 80 dB per decade. So, this is the response of a true first order system, and this is the fake first order system. All right. But as you can see here, at the frequency, so at what frequency does, in this particular example, at what frequency does the behavior of the fake system deviate from the behavior of the true system? At omega 1, correct. And at omega 1, the gain is in this example, what is the gain of what is the gain of the fake omega? At this point, at the point at which the deviation occurs, what comment can we make about the magnitude of the loop gain at that point? It is way smaller than 1, right. And if the magnitude of the loop gain is way smaller than 1, right, for all practical purposes, the feedback loop is not effective, because remember that the feedback loop is only effective when the loop gain is much larger than 1, and on the when it is about 1, right. If the loop gain becomes very small, that 1 plus loop gain simply becomes 1, and therefore does not influence for all practical purposes, it cannot influence stability at all, because for the system to become unstable, 1 plus loop gain must be equal to 0, right, at some frequency. But and we know that up to this frequency, this behaves like the fake the fake system behaves like a true first order system, which we know is stable, right. Now, at omega u, at omega 1, the response of the fake system deviates from that of a true first order system. But at that point, the magnitude of the loop gain is already much smaller than 1, correct. So, 1 plus loop gain, that loop gain being much smaller than 1, whatever the value that loop gain takes, the denominator polynomial can never become 0. Does it make sense? Okay. So, the moral of the story is that to be able to have a large DC loop gain, right. What we did was deliberately introduce a new pole omega d such that omega d is much smaller than omega 1. And what is the meaning of much smaller? I mean, omega d is much smaller than omega 1, and what this much smaller means is that at the frequency at which the frequency response of the fake system deviates from that of a true first order system, right, the gain, the magnitude of the loop gain must be much smaller than 1, right. So, let me write that down. So, omega d is called the dominant pole, okay, and why? Because the response due to omega d dominates the entire frequency response curve, correct. So, omega d is the dominant pole frequency, all right, and omega d must be chosen so that at the frequency at which loop gain of s times 1 by 1 plus s over omega d deviates from true first order behavior, the magnitude of the loop gain must be much smaller than 1. Right. Okay. So, I mean, it turns out that this process of stabilizing an otherwise unstable feedback loop is called compensation, right. So, this is I mean, there are many ways of compensating. This is one way, and this is where because this uses a dominant pole, this is called dominant pole compensation. And the basic idea is to make the third order system or a high order system look like a first order system for all within quotes practical frequencies, right, simply because I mean, what is the meaning of practical frequencies? I mean, in other words, over what frequency range do we want to make the system look like a first order system? It can never be a true first order system. You understand that, correct? Why? Why? You tell me the question. Huh. Got nothing to do with. No, all I am saying is loop gain of S divided by 1 plus S by omega d can never be a true first order system. The question I am asking you is why? Huh? Yeah, I mean loop gain, so it carries this loop gain of S over 1 plus S by omega d can never be a true first order transfer function, because that loop gain function has got multiple poles inside, correct. In this particular example, the loop gain has got 3 extra poles, right. So, truly it is a fourth order system. Does it make sense, right? However, what by putting a sufficiently low dominant pole frequency, what we have done is make this fourth order system behave like a first order system over an interesting frequency range. And what is the frequency range of interest? Yes. Yes, Nandita. Yeah, so basically the interesting frequency range is the frequency range over which the magnitude of the loop gain is greater than 1 and in the neighborhood of 1, because there we know that 1 plus loop gain can do strange things if the loop gain is doesn't closely match that of a true first order system, correct. So, what we do therefore is the idea behind dominant pole compensation is to deliberately introduce a pole omega d at a frequency so much lower than all the other poles in the loop gain function, so that the loop gain function resembles that of a true first order system over a frequency range which is of interest to us, namely that frequency range where the magnitude the loop gain function is greater than 1, right, and maybe a little bit below 1. All right. Okay. So, we are not really worried about the fact that at very high frequencies there is a deviation between the true behavior of a the behavior of this system, this dominant pole compensated system, and a true first order system, because at that frequency where the deviation occurs, the gain of the loop gain has become so small that it is inconsequential. Is that clear, folks? Okay. So, okay. So, now so for all practical purposes in this particular example we see that you not only got the large DC gain, but you also have the stability corresponding to a first order system, right. Does it make sense? So, but what have we paid for in the process? Yeah. So, basically remember that when we had the pure third order system, the magnitude of the loop gain was very high all the way up to omega 1. But right now, we see that the loop gain started falling off even at at omega d. So, at this frequency for instance, there is a big drop in the loop gain function, correct. Okay. So, the price we are paying for stability is that the bandwidth over which the loop gain is very large has come down significantly, but that is a worthwhile trade off, because earlier the system was simply unusable because it was unstable, right. Now, at least you have a stable system, all right. So, so now that brings up the question. So, basically, so if the dominant pole if omega d is such that the loop gain can be approximated by A1 cube f by 1 plus s over omega d. Now, what comment can we make about the unity gain frequency of the loop gain function? A1 cube f times omega d. What is the 3 dB bandwidth of the closed loop transfer function? Is what? Is the same thing, say 1 cube f omega d, just like in the first order case. Is that clear?